We're going to transition from adding and subtracting vectors into their multiplication. So there are a few ways that you can multiply vectors, and we've done one already. The first was scalar multiplication, where you took a vector and you just multiplied it by a number. So hence the scalar multiplication. So that might be something that looks like 3 multiplied by 2 comma minus 1 comma 5. And all you had to do there was to triple all 3 of the coordinates and get you 6, -3, 15. So that's a scalar multiplication because you're just throwing a single number into the bracket. The next thing we're going to attempt here is some vector multiplications. Okay, so I'm going to take this vector here, 2 comma -1 comma 5, and we're going to take another vector, 3 minus 8 minus 4. Okay, I'm going to write it twice just because there's a point I want to make about it. 5, and then 3, -8, -4. So this is a bit tricky. All right, how are you going to multiply this vector by this vector when you have an assortment of numbers all separated by commas? And there are a number of different ways that you can do it. So the choice you need to make is, do you want, at the end of this multiplication, do you want a scalar as your answer? Like, do you want this to be equal to 8? Or do you want it to be equal to a vector when you're done, like 8 comma 3 comma 2? So the way, what you want as your answer determines which method you use for multiplication. So if you want a scalar as an answer, you're going to use a thing called the dot product. The dot, because we use a dot in there to show that that's the type of operator I'm doing. If you want a vector as an answer, vector, then the symbol I'm going to use here is an X or a cross. So this would be a dot product, and this would be a cross product. This particular video is going to talk about the dot product, or the inner product as it's known, between two vectors. And we're going to do some applications of that and to try and explain what that scalar means when you get your answer. This one, the cross product, will be 2 videos from now. So if you want to take a look at how to do that, you can, well, you'll get there eventually. So this one, just to be clear, I'm going to leave this one for later. Leave for later. And we're going to do this particular product here. So since I'm leaving this one for later, I'm just going to wipe it off the board. So keeping in mind that I want this to be not a vector when I'm done, I'm going to look at each component, right? X and X, Y and Y, and Z and Z. And in order to do a dot product, right, or an inner product, I'm just going to multiply the X's together, multiply the Y's, multiply the Z's, and then add them all up. So in this particular example, I would have 2 times 3 plus -1 times -8 plus 5 times -4. So 2 times 3 is 6, -1 times -8 is 8, and 5 times -4 is -20. For a grand total of 6 and 8 is 14, minus 20 would be -6. So 2 comma -1 comma 5, dot product 3 comma -8 comma -4 is negative 6. It's not a complicated operation. What's tricky is now trying to understand what that means exactly. So I'm going to do a few more just so that you can get a handle of how to do the calculation, and then we're going to launch into what exactly that means. So I just wanted you to take a look at what's here. We started with a vector, we started with another vector. I wanted a scalar as my answer, and this particular operation happens to render that down as one. So I'm going to clear this off, and we're going to do one more dot product, and then we'll talk about what that means. All right. So presented with this particular question, I have a vector, and I have a vector, and they are connected by a dot. So when you see that dot, you need to train yourself to see it as a dot product, and know that when I'm done this, my answer needs to be a number, right? Just a scalar, no commas, no vectors, nothing left. It's just a normal number like 8 or what have you. So to execute this, I take the x values and I multiply them, 6 times 4, and then the y values, 2 times 2, and then the x values, or sorry, z values, negative 3 times 3, gives me a total of 24 plus 4 minus 9. 24 and 4 would be 28, minus 9 would be 19. So 6, 2, negative 3, dot product with 4, 2, 3 is equal to 19. All right. So you can do the calculation. It's not challenging, but what we need to figure out is why, like what's happening here. Okay. So I'm going to clean this off. And I'm going to draw these two vectors for you, and then maybe we can figure out what's going on here. So 6, 2, negative 3 goes this way, and 4, 2, 3 goes that way. All right. So this number, when you're doing a dot product, is trying to give you a value for how parallel these vectors are. That's not exactly right, but it's close. So the closer these two things are to being lined up, the bigger this number gets to be. So if you look at this particular one, and I just made it up, what I'm trying to get is how big is this angle, right? Like there's a relationship in there between this angle and how long this is and how long that is. So with you could do a big complicated algebra proof, and I don't want to do that. But when you put this all together, right, like the length of this thing, if this were longer, you'd be covering more of this vector. If this angle were narrower, you'd be covering more of this vector. These three ideas, if you wrap them all up together into one little equation, you end up with this vector here. Call that one A. And this vector here. That product is giving you the size of A multiplied by the size of B multiplied by the cosine of the angle between them. That's what this number is. So if I was given the two vectors in vector notation, I can calculate the magnitude of that. That would give me A. I could calculate the magnitude of that. It would give me the magnitude of B. I can do the dot product manually and end up with a number here. And the only thing that's left for me to solve then is cosine of the angle between them. So what I've got here is a way to use the dot product to calculate the angle between two vectors. So if I were to do that with this particular one, the magnitude of A is going to be the square root of 6 squared plus 2 squared plus negative 3 squared, which is the square root of 36 plus 4 plus 9. 36 and 4 is 40 plus 9 is 49, and square root of 49 is 7. That's handy. Magnitude of B would be square root of 4 squared plus 2 squared plus 3 squared. 4 squared is 16, 2 squared is 4, 3 squared is 9. 16 and 4 is 20, plus 9 is 29. Square root of 29, now that's awful, but it'll do. And I already went through and did this and figured out that A dot B was 19 if I did the dot product manually. So if I were to take this little structure here and fill in A dot B, magnitude of A, magnitude of B, I should be able to get the angle between those vectors. I'll write it down there for you. Okay, so A dot B was 19. Magnitude of A was 7. Magnitude of B is root 29. And cos theta is the thing I don't have. Alright, so I'm going to divide both sides by this. And so the angle between them then is the arc cos of 19 over 7 root 29. Whatever that is. Now that's the exact answer. If I want to get the answer in a decimal, I'm going to do it in degrees first, just because degrees are a little less confusing for most people. How do I do that? So 19 divided by 7 is 2.7, divided by the square root of 29 is 0.504. So if I arc cos that, arc cos of my answer, I get 59.73 degrees. Now, anytime you use arc cos, you're supposed to get a second solution, right, by cast rule, C-A-S-T. So I had a positive, so that's either here or it's here. So my other solution would be 360 degrees minus this, so let me work that out. 300.267. Okay. So what I've just calculated there is that this angle is 59.73, 59 degrees, or it's 300. And you notice that if this is 59, then that's the 300 degree solution. Okay, so if you were to take this vector and have them leave the same point in space, they would do so at a 59 degree angle. Now that's kind of neat, because it doesn't have to be on a flat surface, right? It could be 59 degrees in any particular orientation. So this dot product is allowing you to get that angle even though it's on two sort of abstract things that you'd never be able to put a protractor on. So if you had wires, guide wires, or roof rafters, right, that not only rise vertically but also sometimes diverge this way at the peak or in a valley of your roof, you can calculate the angle that those things meet at if you have to cut the piece of wood to actually lay on top of them by using vectors, right? Where do they start and then the coordinates of how far in x, how far in y, and how far in z each rafter goes from that start point. All right, I'm going to clean this off. I'm going to do one more example of that that's a little more straightforward, top to bottom, and then we'll try going the other way. Okay, so determine the angle between this and this. So the tool I have that finds the angle between two vectors is the dot product of those two vectors equals the magnitude of the first, magnitude of the second, cosine the angle between them. All right. So I'm going to need to get three things in order to answer this. I'm going to have to get the magnitude of m, the magnitude of p, and then I'm going to have to execute the dot product between m and p manually by doing x's times x's, y's times y's, z's times z's. So if I do that in that order, see, the magnitude of m would be the square root of 6 squared plus negative 3 squared plus 2 squared is 6 squared is 36, minus 3 squared is 9, and 2 squared is 4. This is the square root of 49. I keep getting that. Square root of p would be the square root of 4 squared plus 3 squared plus 1 squared, which is 16 plus 9 plus 1, should be the square root of 27. And m dot p, if I execute this manually, will be 6 times 4 plus negative 3 times 3 plus 2 times 1, which is 24 minus 9 plus 2 is 24, 26, 17. 27. 24 minus 9 would be, no, I was right. Never second guess yourself, it leads to mistakes. 24 minus 9 would be 15, plus 2 is 17. There we go. Okay, so filling that information into this particular object, I have 17 is the magnitude of m multiplied by the magnitude of p and the cosine of theta. So working that out, I'm going to bring these two things into the denominator. And 17 divided by 7 divided by root 27. .43 divided by square root of 27. 0.467. And I'm going to arc cos that. 62.1 degrees. So wherever m is headed and wherever p is headed, the two of them meet at a 62.1 degree angle. All right. That's pretty straightforward. So now that you can get the angle between two vectors, I'd like to talk about the idea of vectors being parallel. So I'm just going to erase this, and then we're going to start with this, and we're going to talk about those things. All right, this word here, perpendicular, that means that they meet at 90 degrees. Meet at 90 degrees. So this little structure here gives you a handy way of checking if two vectors are perpendicular. Because if you put 90 in there, you try cosine of 90. The cosine of 90 is 0. So if, let me write that out for you, if M and P are perpendicular, then cos theta would be 0. If cos theta is equal to 0, then magnitude of M magnitude of Q times 0 would be 0. Right? 0 times those two things go away. Therefore, M dot Q would equal 0. So because the dot product is giving you the magnitude of one vector times the magnitude of the other multiplied by the cosine of the angle between them, if that angle happens to be 90 degrees, then this thing is going to zero out on you. So let's give that a try. Let's just see what M dot P is. M dot P would be 5 multiplied by -6 plus 1 times 2 plus 8 times 5. So that would be -30 plus 2 plus 40, which is 12. So if they were perpendicular, then I shouldn't be ending up with 0 there. So this is not equal to 0. Therefore, M and P are not perpendicular. Okay, good. So if I can just test if something is perpendicular using dot product, I can also use dot product to try and force two vectors to be perpendicular. So I'm going to erase this and I'm going to give that a try. Okay, so to do that, first off I'm going to have to make up a vector, right? I'm going to start off with this thing, that 3, -4, 2, dotted with a vector that I don't know anything about yet, except that I'm trying to make it perpendicular to this. We're going to use the fact that cosine of 90 would be 0. So if this thing is perpendicular to that, then this dot product has to be worth 0. Now that's very complicated. I have 3 letters and only one equation. If that happens to you, you have too many degrees of freedom. So I'm going to have to actually choose 2 numbers randomly and then use those 2 numbers to calculate the third. So what's your favorite number for x? What's that? 7? Okay. So choose x to be 7, and let's make y 5. Why did I pick these numbers? For absolutely no reason. I just chose them because I can. So I'm going to do this dot product with those 2 numbers filled in, and then I'm going to use the mess that I make to figure out what z would have to be so that these 2 vectors were perpendicular. So dot product, 3 times x, that would be 3x, minus 4 times y would be like this, 2 times z equals 0. Now, if you go to the end of this course and you watch the sections on planes, you're going to find that this is the equation of a surface in 3 dimensions. Now, you don't have to know what that means quite yet, but basically it means that this vector here goes out through space and there's a whole sheet of vectors that are perpendicular to it. from this vector, you can go in any direction you like. And as long as these coordinates do it in the right combination, you can leave this vector perpendicular to its surface in an infinite number of directions. Sort of like hanging a key on a string, right? You can spin the key and it will point in any direction you like, and it's going to remain perpendicular to the string as it does it. So I've already done this here. I've chosen an x and a y, so I'm just going to plunk them in there. 3 times 7 minus 4 times 5 plus 2 times z. 3 times 7 is 21. 4 times 5 is 20. 21 minus 20 is 1. Kick this over. 2z equals negative 1. Z equals negative 1/2. So if I have a vector that's going 7 in x and 5 in y, and I make the z go down 1/2, I will have constructed a vector that is perpendicular to this. And just to check your work, throw that thing in there, dot product it, and if you've done your work correctly, this should end up giving you 0. So 7 times 3 would be 21. 5 times negative 4 would be negative 20, and half of 2 is 1. Negative times positive is negative. Gives me 0. So indeed, I have come up with a vector that is perpendicular to 3, negative 4, 2. You notice that the question didn't ask for 1, it asked for 3 vectors. So that's one of my options. Let's write that up here. 7, 5, negative 1/2. Okay, so I did one where I picked the x and I picked the y. So I'm going to do one that I picked the y and the z instead. I'm going to get rid of this, and I'm going to ask you what your favorite numbers are for y and for z. And I'm going to hear you screaming from out there in the internet that your favorite y value is negative 4 and your favorite z value is 1. Great. I like those numbers. So I'm just going to plunk these into this equation, right? This equation of a plane. And I'm going to work out the x that would make this vector perpendicular. So 3x minus 4 times negative 4 plus 2 times 1. It's 3x plus 16 plus 2. 16 and 2 is 18. Kick that over. Divide by 3, x is negative 6. So if I pick a vector that has a negative 4 for the y and a 1 for a z, I just calculated that putting a negative 6 here will force that vector to be perpendicular to this one. And if I check it, which is always good habit, negative 6 times 3 is negative 18. Negative 4 times negative 4 is plus 16. 1 times 2 is 2, and indeed, those add up to 0. So here's another one. Negative 6, negative 4, 1. So I did one by assigning x and y. I did one by assigning y and z. So I'm going to do one where I assign x and z then, so that I've done all 3 combinations. Not for any reason, just because I like to do it that way. So let's see, internet. How do you feel about x is minus 5 and z is minus 8? Okay, in they go. 3 times negative 5 is 4 times y plus 2 times negative 8 equals 0. That's 15. It's negative minus 4y. 2 times negative 8 would be negative 16. Negative 15 minus 16 would be negative 31. bring that over. So I'd have 31 over 4, which is 7.75. So if I make a vector that has -5 as its x and -8 as its z, if I make this thing in the center -31/4, then I have constructed a vector for the third time that is perpendicular to this. So again, just to check, 3, -4, 2. That would be -15. -31/4 times -4 would be +31. And -8 times 2 is -16. And those things equal z, or 0. So -5 minus 31 over 4 and -8 is also perpendicular to 3, -4, comma 2. Now, if you think about what's happening here, how many numbers could you have picked for x? How many are available? And the answer is infinity. You can pick, there's an infinite number that you can have there. There's an infinite number you can have for your second. So there's an infinite number of vectors I could crank out here that are perpendicular to 3, -4, comma 2. And we were only asked to find 3 of them, so that's fine. All right, good. So the last thing we're going to do in this section is to figure out how to do the projection of one vector onto another and see what that means. All right, so with this thing, I'm going to give you an A and I'm going to give you a B, and I'm asking you to do a thing called the projection of A onto B. And the way we're going to write that is either projection onto B of A, or you might see it simply as A projected onto B. One of these two notations you'll come across. So it's just an equation, so I'm going to write it up there. We're going to do it so you can see how to do it, and then we'll talk about what it means. So the projection onto B of A would be A dotted with B divided by B dotted by B multiplied by vector B. Gross. But it's just something you can do, no problem. So this thing then, the projection onto B of A would be A dot B. So I'm going to take my x times my x, -3 times 2, there's my marker, plus 2 times 5, plus 4 times 6, divided by B dot B. So it'd be 2 times 2, 5 times 5, 6 times 6, all right, so -3 times 2 would be -6. Oh, and then I've got vector B back here. Plus 10, plus 24. And 2 times 2 is 4. 5 times 5 is 25. 6 times 6 is 36. Projection of B on, or A onto B. 10 and 24 is 34 minus 6 would be 28. 25 and 36 is 61 plus 4 would be 65. See, neither of those divide by 3, 4, 5, 6, or 7. Okay, so I think we're done. So after this little formula, I've asked you to do the projection of A onto B, and I got some fraction of vector B. So I'm going to draw for you the diagram that we had in the first place. I had A going here, and I have B going here. Something like that. And these two vectors meet at some angle. And now I've got this little thing here. Do you notice that this is a scalar, right? It's just a number. It's about half multiplied by a vector. So a scalar times a vector takes that vector and either stretches it or shrinks it. And for this one, because it's well, I'm gonna render that as a decimal just so you can see. 28 divided by 65 is approximately 0.43. So because this is less than 1, it's going to take that vector and it's going to shrink it to about this length. Now, do you notice that that length and this vector happen to form a triangle that happens to have a 90-degree corner? So this thing, the projection of A on B, is asking you how much of A is parallel to B. Or if you were to tip this flat and let the sun shine down on top of it, where would the shadow of vector A lie on top of vector B? So you're trying to figure out how much of this thing is headed in that direction. It says, well, this vector A is made up of this much of vector B. You need 0.43 B's in order to get the horizontal component of that particular vector. All right. So if I were to try and take this and make it a little more general, I'm going to erase this and we'll think about that and give her a go. Okay, so I'm going to start with this here, this B dot B. So it doesn't matter what B is. If you do B dotted with itself, you end up with the x component squared plus the y component squared plus the z component squared. Now that looks very familiar. The x squared, the y squared, and the z squared all added together, that's the magnitude of this thing. I'm missing a square root. So this is the magnitude squared. So I'm going to make that change down here. A dot B up here is just this thing, so I'm going to fill that in. And you notice I have a magnitude of B over top. Oops, sorry. Notice I've also left out the cosine of the angle between them. So you notice that I have a magnitude of B up here and a magnitude of B down here that are going to end up undoing each other. And so what I've got left then, projection onto B of A, would be the magnitude of A cos theta. And I'm going to bring this magnitude of B underneath of this one. Now, what I've got here then is I take this vector b and I divide it by its length. So what I'd have then, vector b divided by its length, if you divide anything by its own size, you end up with something that has a length of 1. And if you have a vector that is exactly 1 unit long, you call that a unit vector, right? It's just 1 unit long. And I note it like this. So that thing is a unit vector, which means length 1, 1 unit, in the direction of b. All right, so I'm going to make that change here. Projection of b a is the magnitude of a cos theta times a unit vector in the direction of b. So I'm gonna draw this for you. First off, I have the projection of a onto b, and then I have a itself, and then I have this mysterious side that happens to meet at 90-degree corners. So I just constructed that. Now, perhaps you remember from basic trigonometry in grade 10 that if I were to park an angle in there, that this side here is adjacent to that angle, and this side is the hypotenuse. So if I were to take this divided by this, I would have the adjacent side divided by the hypotenuse. And that would give me a cosine equals proj b a over the hypotenuse. Now I can't use a here. It's supposed to be the length of the hypotenuse. So the length of that would be magnitude a. Now if I take this and pop it up there, magnitude of a cos theta equals projection of BA. I guess that's the size of that thing. Notice that I've got this same thing here. The only thing I need to make it a vector is to attach this little unit vector that tells me to go that way, but only go that far. So you use this in physics a lot when you're trying to figure out the components of motion, right? Whether something has a vertical component or a horizontal component, or what piece of the thrust of a rocket is going along the path that you want. So that's what this calculation is for. I've tried to strip all the physics out of this class so that you're just doing these calculations. So in the problem set, you're going to be asked to do straight up dot products, find the angle between two vectors, identify some vectors that are perpendicular to a particular one, and then calculate a projection just given the two vectors involved.